What's going on, Science 10s? It's Mr. Walton here. Today we're going to talk about gravitational potential energy. And I don't know if you know this, but potential energy is just energy that's stored or could be used at a later date. So anytime you or somebody else stores energy for later, that's a form of potential energy because it has the potential to be released at a really convenient time. So for example, you take in potential energy all the time. You take in potential energy in the form of food. It's chemical potential energy. You eat certain chemicals like sugars and carbohydrates, and you store that energy for later. You store it for a hockey game, or you store it for, during the day when you're walking back and forth or thinking or something like that, right? So potential energy is energy that's stored and can be used at a later date. Another type of potential energy is gravitational potential energy. Gravitational potential energy is energy stored in objects relative to their height above the ground. Let's take an example. Let's say Mr. Walton here. So we got basically a series of pulleys here. So Mr. Walton uses a winch down here. It's just like a gear, and it's got a cord attached to it, and that cord strings way up over a pulley, and it's attached to a weight. And so when I wind up this gear, it pulls on the cord, and the weight goes up. Now, what we could do is we could figure out how much energy this object has up high here. A bunch of different ways. First of all, when I turn this gear, the cord gets pulled down, so that means the object gets pulled up. So what's happening is I'm performing work on that object. And remember, work is equal to the change in energy of the object. So when Mr. Walton performs work, he's actually transferring energy to that object. This object is gaining energy by getting pulled up. And the type of energy it's gaining is gravitational potential energy. Now, what's happening? Okay, so Mr. Walton's winding this up. He's pulling down on the rope, and the rope is attached to the object. So the object's getting pulled up. But then Mr. Walton locks the gear in place, and the object's just sitting there. So the object's just sitting there, and it's not doing anything. So if it's not doing anything, it doesn't seem like it has a whole heck of a lot of energy. But at any point in time, Mr. Walton could cut that cord. We got some scissors here. Mr. Walton's going to cut that cord. And what do you think is going to happen to that object? Yeah, you're totally right. It's going to come crashing down, and it's going to slam this post further into the ground than it's already been slammed. And so this is one way of driving objects into the ground, okay? So what's happening is Mr. Walton is performing work on the object, and because Mr. Walton's performing work on the object, then the object is gaining energy, and the energy it's gaining is potential energy because we're storing it. I could leave this object here for, 5 minutes. I could store that energy for 5 minutes. I could store it for 3 years. I could store it for 1,000 years. And as long as the rope doesn't break, that energy is going to be stored there for as long as it gets stored there for. As soon as we release it, as soon as it starts to fall, then it starts to unleash that energy, okay? So it's so you can think of it this way. So Mr. Walton is here, and there's a bookshelf. And Mr. Walton's not a particularly tall individual, for those of you that know me, okay? And there's a box on the ground. And Mr. Walton's going to go put it on the second shelf, okay? So it's not very high up off the ground. If that box falls off the shelf, does it have a lot of energy? Does it have a lot of energy sitting there? Well, if it's only on the second shelf, it doesn't have a ton of energy. It's not going to fall extremely quickly. It's not going to hit the ground really, really, really hard. But if he takes that box and if he puts it up on the top shelf, right, above the bookcase, then it's going to have a lot more energy. Which one of these objects or which one of these spots do you think if it were to fall from, is it going to hit the ground with more force or harder? So yeah, you're totally right. When we put the box up at the top versus the box on the second shelf, this one has more potential energy. And we write potential energy as EP. Now, one thing to just keep in mind, this is based off of an object's kind of ability to fall, okay? And so it's going to take into account something that we call G, which is acceleration. We've talked about this before, acceleration due to gravity. And this is in your notes, it's in your data booklet. It's on page 5. But in your data booklet, it says G is 9.81 meters per second squared. And that's because every object in the entire world accelerates when it's close to the surface of the Earth, like within 100 meters or something. Whenever it's close to the surface of the Earth, it will accelerate at the same rate. Doesn't matter if it's a feather, doesn't matter if it's a bowling ball, doesn't matter if it's a human being, it'll accelerate at a certain rate. But that's only if we kind of ignore things like wind resistance and stuff, okay? So we're simplifying a little bit, but just keep that in the back of your mind. Now, there's an equation that we can use in order to calculate the potential energy of an object. The equation that we're going to use is EP, remember that's potential energy, is mgh. And what that means, so this is the potential energy, obviously. Potential energy. M is the mass of an object measured in kilograms. G is the acceleration due to gravity, right? It's not the force of gravity, it's not gravity, it's the acceleration due to gravity. And then H is the height above ground. Or we could say it's the height above like a reference point if we wanted to, right? So let's say Mr. Walton picks up a box, off of the floor, but let's say he's on the second floor of the house. We're just referring to, the height above a certain reference point. That's what we're thinking of. And it's going to be measured in meters. Now let's figure this out. What are the units for potential energy? Well, it's energy, right? And what's energy measured in? Well, it's joules, or capital J, or a Newton meter, right? Or a kilogram meter squared per second squared, that kind of thing, blah, 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 blah. You know the drill. So we're going to go through 2 examples, and then I'm going to let you loose, and then I'm going to get you to do some questions for moi. Here we go. Potential energy number 1. How much potential energy does a 0.85 gram rock have when it's raised 0.92 meters above the ground? Okay, you know the drill by now. Squiggly line. How much potential energy? EP equals question mark. Does a 0.85 gram rock is? Ooh, that's awkward. That's super awkward. Uh-oh. What do you notice here? It's not in the right units. So this is in grams, and we need to convert it to kilograms. And when we go back to our data booklet and we see, okay, grams and kilograms, there's a difference of 3, right? So I want to turn this small unit into a big unit. I'm going to have to move 0.85 to the left 3 times. So it's going to turn into 0.00085 kilograms. Okay. So the mass is 0.00085 kilograms. No problem. Here we go. When it is raised 0.92 meters above the ground, so its height is 0.92 meters. And something that they don't give you, but it's been raised off of the ground, and anything raised off of the ground has the potential to fall or accelerate back to the ground at a rate of 9.81 meters per second squared. Here we go. So we want to calculate potential energy. Here, I'll move this back up. Potential energy is mgh. So let's go ahead. It's already arranged. It's already isolated for the variable that we want. EP is all by itself. Good. So 0.00085 kilograms, 9.81 meters per second squared, and 0.92 meters above the ground. Here we go. So when I put that into my calculator, you're going to get not very nice number. When we put that into our calculator, we're going to get 0.0076714, blah, 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 blah. And it's a kilogram meters squared, meters times meters. But, I mean, it's energy. It's just a joule, right? Here we go. So, as always, anytime we have an answer, we need a number with correct significant digits and the unit. So what we have to do is we have to round. Here we go, 2 significant digits, 2 significant digits, 3 significant digits. So we got to round to 2 significant digits. So this is going to become 7.6 is actually going to round up to 7. 7.7 times 10 to the 123, -3 joules. Perfection. There we go. So that's how much potential energy a tiny, tiny, tiny little insignificant rock has when we raise it up 0.92 meters above the ground. Now that's going to be important. This doesn't seem super important right now, but we're going to do lots of amazing things with that here in a few days. So let's keep at it. Last example we're going to do. Potential energy number 2, a 55 kilogram, good, love it, diver standing on a diving platform has a gravitational potential energy of 5.40 times 10 to the 3 joules. What is the vertical height of the diving platform? Squiggly line. Here we go. Mass is 55.0 kilograms. Gravitational potential energy 5.40 times 10 to the 3 joules. What is the vertical height of that object or that diving platform? Here we go. One last thing. Remember vertical height, right? Gravitational potential energy, you're always going to have G equals 9.81 meters per second squared. So let's try this. EP equals mgh. Got a little bit of a problem. We got a little bit of a problem. Here, I'm going to write that the way I have been writing it. M times G times H. If we want H, we want the height of this diving platform, we got to rearrange this equation for height. The problem is we got to do the opposite operation. H is being multiplied by M and G here. So what we got to do is we got to divide by both M and G at the same time. You could do them separately if you wanted. You could divide by M and it'd show up over here on the bottom. You could divide by G and it'd show up here on the bottom. And your rearranged equation would look like this. H is EP over mg. And it's the same for any of them. I could have solved for H. I could have solved for M. I could have solved for G if I was like on a different planet or something like that. Remember that G is just the acceleration due to gravity on Earth. But if you're on the moon doesn't have the same gravity, the same amount of gravitational force or acceleration. So it's going to be different. But I mean, that's like rare. Don't worry about that. So the height is equal to EP over mg. So we'll just start plugging in our information. 5.40 times 10 to the 3 joules on top, divided by the mass, 55.0 kilograms, and the acceleration due to gravity, 9.81 meters per second squared. So when we do this on our calculator, remember you're dividing by two things on the bottom. Anytime you have two things on the bottom of a fraction, or you're dividing by two things, you have to use brackets. Let me show you. All right, pulled up my illegally downloaded calculator. Let's try this out. I'm just kidding. It's not illegally downloaded. It's just a joke. It's just a joke. Calm down. It'll be okay. Shh, it'll be okay. All right. So we got to take 5.4. Remember, it's scientific notation, so we use second EE, right, to the power of 3. So divided by bracket. We're doing two things on the bottom. So 55 kilograms times 9.81 bracket. So that's what's happening. I don't have to write 55.0 because there's no difference between, on my calculator, there's no difference between 55 and 55.0. So let's try that. Nice. 10.00834, blah, 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 blah. And it's in height, and height is measured in meters. Nice. So here we go. Every time we write an answer, we got to have a number with appropriate significant digits and a unit. So we got a number with a unit, but not the appropriate significant digits. 3 digits divided by 3 and 3. So we need 3 digits. The 0 is not going to round. So we are going to get a height of 10.0 meters. Nice. Okay. So the hardest part about that question was rearranging this equation. And what I want to show you just really quickly, just kind of as an addendum here, blah, is we could rearrange the EP equals MGH formula for anything, for any of these variables. If we wanted M, we would divide by G and H, divide by G and H. So M is EP over GH. No problem. If we wanted to get G by itself. So if we wanted to get G, because we're on some other planet that doesn't have the same gravity as us, we divide by M and H, 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 M, M, divided by M and H. So G is EP over M and H. So, I mean, you've got your kind of 3 rearranged versions of the equations there. So what I want you to do is we've got 5 questions here. So questions 1, 2, 3, 4, and 5. And I would like you to try and answer these questions. Question number 4 doesn't have a ton of math involved, but just try and think it out, right? And the way I want you to think it out is go back to the idea of me putting something on the shelf, right? So it's saying 2 objects have different masses. So there's a box here and there's a box here, right? There's a tiny box and a little box. And Mr. Walton wants to put them on the same shelf. So the height above the ground of the heavier box, 2 objects of different masses have the same potential energy. So I'm going to put them on my shelf, and one box is going to be here and one box is going to be up here, right? And so the height above the ground for the heavier box must be what in order to have the same potential energy? Just try and think about it, and we can reason it out. And look at the key. Look at the filled in notes for the answers, and let me know if you have any questions. Down here it says that there's additional practice here. You by no means do you have to do them. That is totally optional if you even have your textbook, right? So there's 5 questions here. Let me know if you have any, or if you need any help or whatever. Anyways, have a good day. Have a good weekend. I'll see you later.